Now let's talk about a statically indeterminate problem. It is designed myself and hope you enjoy it. Two solid cylindrical bars AC and CD of equal length L are welded at C. That is, for AC, its length is L. For CD, its length is also L. The whole piece AD is clamped to the fixed ends at A and D, so those two ends are fixed. Bar AC is drilled such that the segment AB is a hollow circular tube. So in this part, it is a hollow circular tube, and it is connected to a solid cylindrical shaft. We now define some dimensionless quantities. Let D2 equals to PD3 equals to PD, where P is greater than 1. That means the diameter of sections 1 and 2, I mean the blue bar, is greater than that of the segment CD, which is the brown bar. So for the brown bar, we can write it this way. We can draw a table over there. So talking about the diameter of the brown bar is D, while the diameter of the blue bar is PD, where P is greater than 1, means that the diameter of the blue bar, or the outer diameter of the hollow circular bar, is greater than that of CD. Besides, the shear modulus of segment CD is G, while the shear modulus of AC is QG, where Q is less than 1. That means the strength of the blue bar is lower than that of the brown bar. Besides, we also define the ratio between the drilled length of the blue bar to that of the entire length. So consider this blue bar, it is drilled in the middle. We call the length of the drilled segment to be L1, and we know that L3 equals to L1 equals to L. That is, the length of the entire blue bar is L. So S equals to L1 divided by L less than 1. So those dimensionless quantities will be used in part B of this problem. First, let's consider an easy problem in part A. A torque of 500 Nm is acting at point C. Here we just mark it in this double arrow pointing to the left hand side. F L1 equals to L2 equals to 1/2 of L equals to 300 mm. That means the length of the drilled part equals to that of the undrilled part. L1 and L2 are equal. Besides, G1 equals to G2 equals to 35.04 gigapascals. So it is the material property of G1 and G2. G3 equals to 157.95 gigapascals. The material property of the brown bar is much more stronger than that of G1 and G2. Given that the diameter of the blue bar is 30 mm, that is also the outer diameter of the hollow circular segment. D3, which is the diameter of the stronger brown bar, is given by 20 mm. Besides, you are also asked to verify that in case the reactions at fixed ends A and D are the same, then we have the relationship P to the power 4 plus S minus 1 divided by QP to the power 4 times P to the power 4 minus 1 equals to 1. Consequently, I will ask you to verify that your answers in part A is reasonable. I can give you a little hint here. The reaction at A and D in part A should be the same because all the given conditions here satisfies this equation. So it is a very important hint to you in case you cannot get the same answer of the reactions at A and D, you can still get some marks from B and C. Besides, there is a difficult problem for you to think of. If a torque is acting at point C still, Find the threshold value of P such that it is impossible that directions at A and D are the same. That is, under the allowable range of the ratio between the material strength, how large the diameter of the blue shaft should be such that directions at A and D are impossible the same. To do part A, first we consider the statics. By using the statics concepts, we know that TA plus TD equals to T. Bear in mind how to read this diagram. For this diagram, you still can imagine that you are using your right hand to rotate, to twist this tube in the middle, then your thumb is pointing to the left hand side. Consequently, on the fixed ends A and D, there will be a resisting torque, TA and TD, which is trying to rotate this rod back to its original torsional displacement. That is, when you try to twist this bar back, then for TA and TD, by using your right hand, the thumb is pointing to the right hand side. Apart from that, so this is all what we can know from statics. Next, we have to obtain additional equations to solve the statically indeterminate problem, because obviously we can draw no conclusion from this statics result. However, one thing you can bear in mind is that the torsional displacement of C relative to A plus the torsional displacement of D relative to C should be 0. That is, from A to C, the torsional displacement is like this. Then, this is just phi of C relative to A. Then, from C to D, the torsional displacement will be going like this. So this is called phi of D relative to C. Since both ends are fixed, that means the torsional displacement at those two ends are 0. Now we have the compatibility equation obtained from the torsional displacement. Now we find the polar moment of inertia of each of the cross sections. The polar moment of inertia of segment 1, which is the hollow circular segment, is given by this equation. Then you substitute the values. The outer diameter of AB is 30 mm, while the inner diameter is 20 mm as mentioned in the problem, because the diameter of the inner part is the same to that of the bronze shaft. For J2 and J3, similarly, you can obtain the sectional properties in this way. Next, we compute the torsional displacement of each segment one by one. For segment BA, the torsional displacement at B relative to A equals to minus TA L1 divided by G1 J1, because for AB, this hollow shaft, it looks like there is a TA here and then applied torque T here. Since both of them are pointing into the material, that means the torsional displacement caused by the torque is negative, and consequently this torque is a negative torque. Therefore, we have the negative sign located here. By substituting all the possible values into it, and what we left is just the TA. The torsional displacement at point B relative to A equals to minus 2 divided by 4745 pi times TA divided by meter. Similar for phi C relative to B, the torsional displacement at point C relative to B equals to minus TA times L2 divided by G2 J2, but you know G1 equals to G2, so those are the same. Substituting all those values inside, then we have this complicated result. Finally, we sum both of them up to get this result. The torsional displacement at C relative to A equals to minus 4TA divided by 5265 pi Newton meter. Next, we consider the torsional displacement from C to D. We substitute the shear modulus of D as well as the polar moment of inertia into it. Then we will get this. The torsional displacement of D relative to C equals to 40D divided by 5265 pi Newton meter. By using the compatibility equation, we can get this result. That is, we substitute our torsional displacement of D relative to C as well as the torsional displacement of point C relative to A into this compatibility equation. Then this compatibility equation is converted to equation of TA and TD, which are two unknowns that we are going to find. Obviously, from this equation, you can see it gives you the result of TA equals to TD. Since TA plus TD equals to 500 Newton meters, as mentioned in the statics part, then we can find the torque at point A and D. At both point A and point D, the fixed wall gives a positive torque of 250 Newton meter to this shaft. At both A and D, the fixed wall gives the torque of 250 Newton meters. Consequently, the torsional displacement at point C is given by this. Then you just substitute our TA into this equation to get our torsional displacement, which is negative 3.464 degrees. Next, let's talk about this very algebraic problem. It involves a lot of dimensionless quantities. It is given that the reactions at fixed ends A and D are the same, which means TA equals to TD equals to 1/2 of the applied torque, which is T divided by 2. Consider the polar moment of inertia of both cross-sections and try to express it in terms of those dimensionless quantities. D2 equals to PD3 equals to PD. Then we just substitute it into it to get P to the power 4 times D to the power 4. Well, D3 is simply D, then it is just D to the power 4. Then you will have this content in this bracket. Similarly, the polar moment of inertia of cross-sections 2 and 3 can be found in this way. Now we evaluate the torsional displacement on the segment AC. Similar to what we did previously, we first find the relative displacement of B relative to A, then find the torsional displacement of C relative to B. You substitute the torque into it, as well as the length modulus and the cross-sectional properties. Then you find the torsional displacement of B relative to A equals to this. Similarly, for the torsional displacement of C relative to B, first you place your torque into it, but notice that what is L2? We know that L1 equals to SL, then L2 equals to L minus L1, which is 1 minus S times L. We also place this polar moment of inertia into this expression, then we get this result. Consequently, by a lot of calculations, you will find the torsional displacement of C relative to A, which looks like this. By very similar manners, we compute the torsional displacement from C to D. Finally, we substitute both the results into the compatibility equation. Then we can have such kind of expression. By simplifying it, we can have the result that we are going to prove. In part C, we are going to verify that our answers in part A is reasonable. It is shown in part A that the reactions at A and D are the same. Now we are going to use the result in part B to verify that it is reasonable. First, check the ratio between D2 and D3, which is the ratio between the blue bar and the brown bar. The ratio equals to 30 mm divided by 20 mm, which equals to 1.5. Next, by considering the ratio between the shear modulus G1 divided by G3 equals to 1168 divided by 5265. Consider the blue bar. The ratio between the drilled length to that of the entire length equals to 1/2. Then we compute the numerator and the denominator, and we get the same result, which is 4.5625. By the numerator dividing the denominator, we have the value is 1. That is, our equation in part B is completely verified. All the given conditions in part A satisfies the equation in part B. The final answer shows that the reactions at A and D are the same. Consequently, our answers in part A is reasonable. But in this problem, we have a very critical limit. If the diameter of the blue bar is too big, to some extent, the reactions at A and D would no longer possible to be the same. Therefore, we cannot make the diameter of the blue bar too big. Otherwise, it is impossible to make our problem in part A occur. If a torque still acting on point C, find the threshold value of P, the ratio of diameter between the blue bar and brown bar, such that it is impossible that the reactions at A and D are the same. That means we want to make the diameter very, very large, such that this equation is no longer valid. We want to void this equation. By observing this equation carefully, we observe that when P tends to infinity, when P is large, this equation will tend to 0. The result shows that when the denominator is large enough, then we can make the equation void. In another word, if P is large enough, no matter how we adjust the value of Q and S in the allowable range, recall that our allowable range is this. No matter how we adjust Q and S, the equation will become void. Consequently, in order to fight against P, we want to drag the denominator down and pull the numerator up. That is, since we are going to find the threshold value, we will try our best in the allowable range to make this equation valid first, such that when we have already chosen the optimal values of Q and S, we can say, okay, the P we reached will be the threshold value such that it is impossible to make this equation valid. To pull the numerator up and drag the denominator down, let's set Q equals to the minimum value, which is 0.15, and S equals to 1. We expand this equation in this way, such that both sides are polynomials. Then we rewrite this equation in this way. Notice that we can write P to the power 4 as a quadratic term. Put our optimal value of Q and S into this equation, then we can have this inequality. Consider this quadratic inequality with the unknown P to the power 4. Simplify this inequality and solve it, then we can have P to the power 4 is less than 0, or P to the power 4 is greater than 23/3. Consequently, when the value of P to the power 4 is greater than this value, then the equation will become void. Therefore, the threshold value we are going to find is 23 divided by 3 to the power 1/4. The result is 1.664. Notice that the threshold value of P is largely constrained by the ratio between the shear modulus of the blue bar and the brown bar.